Hello, welcome to Farbist Academy. In this video, we will be going over the solutions to the Galois Contest, which is the grade 10 math contest for the University of Waterloo. And it is a contest which is not multiple choice. Students need to show all of their solutions. So we will show you how to do that in this video. The time limit for this contest is 75 minutes, and we will be getting through it in much shorter time than that. So without further delay, let's get that 75 minutes on the clock and let's get started. Members of the art club are between 14 and 17 years old inclusive. The graph shows the number of students of each age in the club. Well, A, what is the total number of students in the art club? So this is simple, just counting from the histogram. We have one 14-year-old, three 16-year-olds, and two 17-year-olds for a total of six. We can say 1 plus 3 plus 2 equals 6. What is the mean? Determine the mean or average age of the students in the art club. So a weighted average would be 1 times 14 plus 3 times 16 plus 2 times 17 divided by the total number of students. So that's equal to 14 plus 48 is 62 plus 34 is 96 over 6 is 16. Part C, we are told that, or we're being asked to determine the number of 15-year-old students that must join the art club so that the mean age of all the students in the club is exactly 15.5. So since the mean right now is at 16 and we want 15-year-olds to be joining so that the mean sits at 15.5, which is halfway between 15 and 16, you would expect an equal number of 15-year-olds as the number that are right now averaging at 16. So the answer should be 6, but let us prove it. Let's say X is the number of 15-year-olds that join, and right now the sum of the other students is 96, and this divided by X plus 6 is going to be 15.5. And solving this equation, we get 15X plus 96 equals 15.5x plus 93. And this gives us 3 equals 0.5x, x equals 6 as we expected. Okay, so these are our answers to these three questions, 6, 16, and 6. All right, let's keep going. Number 2, in a magic square, the numbers in each of the 3 rows, each of the 3 columns, and each of the 2 diagonals have the same sum. This sum is called the magic constant. Each of the 4 figures shown below is a magic square. In figure 1, the magic constant is 18. What is the value of n? So if the magic constant is 18, this should be 9, because 7 plus 2 is 9, plus 9 is 18. 9 and 3 make 12, so n must be 6. In figure 2, what's the value of p? So our magic constant is 21. So this number here must be 7. This number here must be 6, because 15, 8 and 7 is 15, plus 7 plus 6 is 21. 11 plus 10 is 21. 8 and 10 is 18. P is 3. P would be 3. Let's just finish this off then. If this is 3, this is 11. Okay, here we know that 20 has to add to the same number as 2r plus 4 to get the same number. So 2r plus 4 is 20, so 2r is 16, r is equal to 8. If 2r plus 4 equals 20, 2r equals 16, r equals 8. Here we have 3u minus 3 this makes 2u minus 2, so we would have a u minus 1 here to make 3u minus 3, which is our magic constant. And then this guy here, so we have this is equal to this. So 12 plus u equals to 2u plus 1, because plus 2 minus 1. So then this gives us u equals 11. U equals 11. And let's, yeah, u equals 11. If we want to finish this off, this would be u is 11, and this is 13, this is 6, this is 11. So the magic constant is 30. This is 23. This would be 7. This is 14. This is 9. This is 8. This is 10. Does that work? 19 and 11 is 30. 24 and 6 is 30. 17 and 13 is 30. This is 30. This is 30. This is 30. 17 and 13 is 30. 19 and 11 is 30. Okay, good. Excellent. So now let us do number 3. Point A has coordinates 10, 15, and C has coordinates 20, 27. Rectangle ABCD has side AD parallel to the y-axis and side AB parallel to the x-axis. What's the area of triangle ABCD? So let's give this a draw. So we have our XY axis like so. We got a rectangle not drawn to scale, but let's draw it like this. This is B because we're told AB is parallel to the x-axis, AD is parallel to the y-axis, and this guy is C, which is 20, 27. So this, the length of this is 12, and the height is 10, or sorry, the height is 12, and the length is 10. So the area of the triangle equals 120 units squared. Now we draw for B the line with equation y equals negative 3 over 2x plus 39 intersects AD at E and side AB at F. Determine the area of the pentagon BCDEF. So it would actually go something like this. The y-intercept's got to be way up there at 39. And then this right here is E. This right here is F. We want to know the area of this pentagon, which we can discover by calculating the area of this triangle and taking it away from the area of the rectangle. So we know that the x-coordinate here is 10, the x-coordinate here is 10. So let's plug that into our equation, y equals mx plus b, and we get y equals 24. This is negative 30 over 2, which is negative 15. 39 minus 15 is 24. So E is 1024. Okay, now let's do the same for F, except for F, we know the Y value is 15. We don't know the X value. So we have negative 24 equals negative 3 over 2x. Negatives cancel, and we get x equals 16. So we have this guy here is 16, 15. And so AE is equal to 24 minus 15 equals 9. And AF is equal to 16 minus 10, which is 6. And then the area, therefore, of the triangle is equal to 9 times 6 over 2, which is 27. So the area of the pentagon is equal to 120 minus 27, which is equal to 93 square units. So this is 93. The line with the equation y equals mx plus b, with m is less than 0, intersects side AB at G and side AB at H. So just call this H, and now let's call this G. And this is now y equals mx plus b. Determine all ordered pairs of integers mb with b less than 50, for which the area of this triangle GAH is equal to negative 8 over m. Okay, this is a very cool question. So we know from before we need to get the y value of G and the x value of H to determine the area of that triangle. The y value of G is simply equal to mx plus b, but x is 10, so it's 10m plus b. And if we subtract 15, this is equal to AG. Okay? We have AH is equal to, let's solve for x. We have mx plus b equals to 15. So then x is equal to 15 minus b divided by m. And then we have that AH is equal to 15 minus b over m minus 10, and 10 is 10m over m. And notice this is equal to negative 10m plus b minus 15 over m. So then area of the triangle, which is this times this divided by 2, is equal to 10m plus b minus 15 squared times negative 1 over m. And this is equal, we want this to be equal to negative 8 over m. Negative 1 over m's cancel. Oh, and actually this should have been divided by 2 because we have the area of a triangle. So we have 10m plus b minus 15 all squared is equal to 16, because multiplying the 2 by the 8. And notice that this is just equal to AG, which is positive. So even though the solution to this is that the left side is plus minus 4, we can disregard the negative answer. And then we have 10m plus b is equal to 19. And so we can say, let's have m and b. If m is negative 1, b would be 29. If m was negative 2, b would be 39. M was negative 3, b would be 49. And these are your 3 different ordered pairs. Okay? Good. So we're on to the last question now. Got through this really quickly. To determine the number of positive divisors of n, we take the exponents on the prime powers and the prime factorization of n, add 1 to each of the exponents, and multiply the resulting numbers together. Okay, so for example, the prime factorization of 280 is 2 cubed, 5 to the 1, 7 to the 1. And so 280 has 3 plus 1 times 1 plus 1 times 1 plus 1 equals 16 positive divisors. How many ordered pairs of positive integers a, b are there for which a, b equals 400 and a is greater than 1 and less than or equal to b? Okay, so first we need to factor, do the factor tree. So 400 is equal to 2 to the 4, 5 to the 2. Okay, 16 times 25. So that means there are 4 plus 1 times 2 plus 1 equals 5 times 3, 15 factors. And these factors, if we were to list them out, we would get this. Uh, 50 times 8 and 5 times 80. 100 times 4, 2 times 200, and 1 times 400. So these are our 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 factors. This pair we're not interested in because we want a to be greater than 1. So then there are 1, 2, 3, 4, 5, 6, and then 20 times 27 factor pairs. Since a has to be less than or equal to b, there's 7. Otherwise, you could have more. You could have 13 because instead of 16 and 25, in addition to 16 and 25, you could have 25 or 16. 20 and 20 wouldn't have a different version, but the other 6 pairs would. But we can just say 7 ordered pairs for which a is greater than 1 and a is less than or equal to b. Part B, determine the number of ordered triples of positive integers PQR for which PQR equals 270,000. Okay, so again, let's do our factor tree here. Might be here a while. Two and 250 and 2 and 125 and 5. Let's say 5 times 5 times 5. Okay, so actually I'll do it properly. So this is 25 and this is 5 and this is 5. So we have, how many 2's do we got? 1, 2, 3, 4. So this is 2 to the 4, 3 to the 3, 3 to the 3, and 5 to the 1, 2, 3, 4. 5 to the 4. Okay? So this is 270,000. So now, what are we going to do with this? Let's free up some room here. You guys will be able to write on paper, so you'll have more room than I have here. So you shouldn't need to erase anything. But let's say P is equal to 2 to the A1, 3 to the B1, 5 to the C1. Q is equal to 2 to the A2, 3 to the B2, 5 to the C2. And R is equal to 2 to the A3, 3 to the B3, 5 to the C3. Okay? We know that A1 plus A2 plus A3, those exponents need to add up to 4. B1, B2, and B3, those need to add up to 3. And C1, C2, and C3 need to add up to 4. So that P times Q times R equals 2 to the 4, 3 to the 3, 5 to the 4. which is 270,000. So solving this equation, so these are the equations we need to solve. Okay, so how are we going to solve these? The stars and bar method is your friend, stars and bars method. If you have 4 objects and you need to put them in 3 bins, that means you need to put down 2 dividers. How many ways can you do that? You could put a divider here, you could put dividers here. So this is 1, or sorry, 0, 1, 3. That is one way of ordering this. So effectively, we need to be able to put, we have 6 entities, 4 squares and 2 dividers. The squares are repeats, the dividers are repeats. So how many ways can we order this? 6, choose 2. So this has 6, choose 2 solutions, which is 15. And this one is the same. This has 5, because 3 objects, 3 ones, and then 2 dividers, so a total of 5 objects. The 2 dividers are repeated, so we have 5, choose 2 equals 10 ways of arranging. Okay, and so there are 15 times 10 times 15. Since all of these, actually, sorry, my mistake. This should be, let me rewrite this. A1 plus A2 plus A3 equals 4. B1 plus B2 plus B3 equals 3. C1 plus C2 plus C3 equals 4. Okay, so since these are assigned independently of these, the number of solutions we have is 15 times 10 times 15, which is 2250. Okay. Okay, now let's do the last one. The last one, C, determine the number of ordered triples of positive integers x, y, z for which x, y, z equals 270,000 and 1 is less than x, is less than or equal to y, is less than or equal to z. Okay, so here, how are we going to do this? So we have some extra requirements that x has to be greater than 1. And x has to be less than or equal to y is less than or equal to z. So let's see how many we need to take away from here where one of the numbers is 1. And when the numbers are on not in order from least to greatest. So first, let's see how many numbers are the number 1. The way to do that is to find factor pairs that can multiply to get 270,000, and then we can just add a 1 to each of those factor pairs to find out how many triples there are that multiply out to 270,000. So remember that 270,000 is 2 to the 4, 3 to the 3, 5 to the 4. So there are 4 plus 1, 3 plus 1, 4 plus 1, 5 times 4 times 5 equals 100 factors. This means there are 50 factor pairs. There are 50 factor pairs. So what are we going to do with that information? Take a moment to think about that. So one of these factor pairs is 1 times 270,000. Okay, let's ignore this for now. And then there are 49 other factor pairs. And these will be unique. Each of those numbers in those pairs will be different from the other because 270,000 isn't a perfect square. So then if we were to add a 1 to this factor pair, we have 3 unique numbers, 1, A, and B, and there's 49 of these, and they each have 6 arrangements. So this gives 294 different triples. Okay. Now, let's think about how many of these ordered triples in here have repeated values. So in other words, going back to the fact that we said that we were saying there we had PQR, but let's say we have XY. Actually, let's just go back to PQ and R. PQ and R, this was 2A to the 1, 3B to the 1, 5C to the 1, it's 2A2, so what are we going to do with this? Well, we know if we were to say that 2 of these numbers were equal, it's arbitrary which we choose to be equal. So let's just say that P and Q were the same. P and Q were the same. If P and Q are the same, this would be A1, B1, and C1. So then we have 2A1 plus A3 equals 4. 2B1 plus B3 equals 3. 2C1 plus C3 equals 4. So the solutions to this, not putting any restrictions on whether or not A has to be bigger or smaller than A1, ignoring restrictions on whether or not A1 has to be bigger or smaller than A3. A1 could be 0, 1, or 2. B1 could be 0 or 1, and C1 could be 0, 1, or 2. So we have 3 times 2 times 3 ways of doing this. Notice within these 3 times 2 times 3 equals 18 ways. This includes the 1 times 1 times 270,000. Okay. So we have to take minus 1. This gives us 17 17 ways of having 2 numbers repeated. Okay. Now, what are we going to do? So we start with 2,250, and we take away the 294 ways of having a triple with a 1, with a single 1. And then for these 18 ways of having a repeated, if we have two entities the same in a list of 3, there are 3 ways of scrambling that. So there are actually 54 ways of having a triple with 2 objects repeated if there are 18 such triples. So after we've taken this and this, that away from this, that leaves us with all of the triples that have 3 unique values, where none of them are 1. We can divide that by the 6 ways of scrambling up 3 unique values to come up with the number of ordered triples, where x is greater than 1, x is less than or equal to y, y is less than or equal to z. Actually, that gives us x is greater than 1, x is less than y, x is less than z. And now we have to add back 17. There are 17 ways of having x bigger than 1, x less than or equal to y, y less than or equal to z. And notice x, y, and z can never be all equal. It's only 2 at most are equal, because 270,000 is not a cube, okay? Because 27 is a cube, but 10,000 is not a perfect cube. So this whole number is not a perfect cube. So our answer is therefore going to be this. So 2250, actually it's going to be easier if I just divide these numbers. 2250 over 6 is 3, remainder 4, bring down the 5, 7, 375 minus 49 minus 9 plus 17. Okay, so this is 326 minus 9 is 317 plus 17 is 334. So there should be 334 ordered triples of positive integers x, y, z, or x, y, z, for which x, y, z is 270,000, and 1 is less than x, is less than or equal to y, is less than or equal to z. All right, so I hope you enjoyed watching this video. We made it way under 75 minutes, and hope this was informative and helpful to you, and I look forward to seeing you in the next video.